Good day everyone. So today I'm going to explain the terms in mathematics. These are the terms, numbers, and conversions. So let's begin with the definition of a number. So a number describes a magnitude or position. Okay, so it has two types, namely the cardinal and then the ordinal numbers. So the difference between the two is that the cardinal is used in counting objects. So for example, we have 1, 2, 3, and so on. So this is a cardinal number. While when we say ordinal number, it states the position. Okay? It is used to state the position. For example, we have first, we have second, third, and so on. Okay, so that's the difference between the two types of a number. Now, we have to take note that a number and numerals is not the same. Okay, they are not the same. When we say numerals, these are the symbols that describes a number. Okay, so the two most widely used numerals are the Arabic and then the Roman numerals. Okay, when we say Arabic, these are the modification of Hindu-Arabic number. So this is the most common symbol of a number in today's era. So just like this symbol, right? We immediately know that this symbols refers to 1, this refers to 2, and this refers to 3, right? So next we have the Roman numerals. These are written in Latin alphabet. Okay? So Roman numerals, these are the Roman numerals. This refers to 1, 5, 10, 50, 100, 500, and then 1000. Okay? Now, if you wonder how to indicate large numbers, these are used in Roman numerals. Okay? A bracket is used to multiply by 100. For example, we have the V, which refers to 5. You're going to add the bracket just like this in a V in order to obtain 500. Okay? Because V is 5 times 100. Therefore, 5 times 100 is equal to 500. Therefore, this is the Roman numerals of 500. Now, vinculum. It is used in order to multiply the number by 1000 times. Okay, so for example, we have the V again. A V, and then we're gonna put a vinculum on top. That's just 5 times 1000. That is equal to 5000. Okay, now if we have the I, or equivalent to 1 times 1000, then this is the, sorry, we have to put the vinculum on top. Then we have 1 times 1000 is equal to 1000. Therefore, this is simply the Roman numerals of 1000, I, and the vinculum on top. Now, if you want to multiply by 1 million, we will gonna use door frame. That's just the combination of a bracket and then a vinculum. Okay, for example, we have the V, that we're gonna put a door frame like this. So 5 times the 1 million, therefore we're gonna have 5 million, and so on. Okay, now let's move forward. I will not be discussing the Roman numerals further because we are just discussing the key terms in mathematics. But just comment down below if you want me to discuss how to express numbers in Roman numerals. Okay, now let's proceed to digits. A digit is a specific symbol used alone. Okay, so for example, we have 3, 5, 6. The 3 is a digit, the 5 is a digit, and 6 is a digit. And say alone, one by one. So in this number 356, we have 3 digits in total. 3 number of digits in total. Okay. Now let's proceed to the categories. Two categories of the number system. We have the real number and then the imaginary number. Okay, so when we say real numbers, these are the classifications of a real number. So we have natural numbers. These are the counting numbers. When we say counting numbers, obviously if you count an object, you don't start with 0, right? You don't start with a negative number. You start with 1, you start with 2, you start with 3. So these are the natural numbers. Okay, now next is the integers. These are all the natural numbers, the counting numbers, and they're negative and 0. Therefore, everything, okay? Negative 1, 0, 1. These are all integers. Next are the rational numbers. These can be expressed as ratio of two integers. Oh, rational, the word rational came from the word ratio. Yeah, ratio, okay? So this includes all the integers and repeating and non-terminating decimal. When we say repeating and non-terminating decimal, that could mean, for example, we have 0.99999. That's continuous. Okay, ellipsis. Okay, that's continuous. That's still a rational number. For example, we have 39, 39, 39, 39. That's still a rational number. Okay, even if it's continuous, but as long as it is repeating. Okay, next one is, or the irrational numbers. This cannot be expressed as quotient of two integers. This is the complete opposite of a rational number. Okay, they are complete opposites. When I say irrational numbers, these are numbers that are not repeating, and then it can also be non-terminating, but it is not repeating. Again, it is not repeating. So for example, we have the pi as as an example of a rational number. We all know that a pi is a 3.14, 15 something, and so on. So this one is not repeating, right? So that classifies the pi as an irrational number. Then when we are going to get the square root of 2, that will be 1.41421356. So this is not repeating, okay? And then and so on. Again, the rational numbers, these are repeating and non-terminating, classifies it as a rational number. But if it's non-repeating or not repeating, then it classifies that decimal number as an irrational number. Okay, next we have the second category of the number system. We have the imaginary numbers. These are often referred as the I, or in electrical engineering, it is often referred as the J. Okay, so this is simply the square root of a negative number, or negative 1. Okay, okay, so I is equivalent to square root of negative 1. So I squared is simply the square of the square root of negative 1. So that's just equivalent to negative 1 raised to 1 half. Yan. Now, loss of exponent, that will be okay, so by loss of exponent, this will just be distributed, so that will become negative 1 raised to 2 over 2. Therefore, that's just negative 1. Okay, 2 over 2 is just 1, right? So, negative 1. Therefore, I squared is just equivalent to negative 1. Now, if we're gonna put I cube, then that will just be equivalent to square root of negative 1 raised to 3, or simply, or that's just simply I squared then multiplied by another square root of negative 1. But we should remember that square root of negative 1 is equivalent to I, right? It's just equivalent to I, okay? Therefore, I squared times I, this will be I, I'm gonna remove that, this will be I, and recalling that I squared is equivalent to negative 1. Therefore, this one will just only be negative 1 times I, or negative I. Therefore, I cube is just equivalent to negative I. Okay? Next, we have I raised to 4. That's just square root of negative 1 raised to 4, or simply I squared times I squared. Now, we all know that I squared is equivalent to negative 1, right? So that's just negative 1 multiplied by negative 1. Therefore, that's just positive 1. Okay? Now, if we're going to summarize that, we just have to remember that I is equal to square root of negative 1. I squared is equal to negative 1. And then I cube is just negative I. And I raised to 4 is just positive 1. Okay? Now let's go to the another term. We have a complex number. These are numbers that is a combination of a real and an imaginary number combined. Okay, so when I say complex number, this is in the form of this format: a plus bj. So the a part is the real number, we have discussed that earlier, and then the b is an imaginary number. This, the bj, okay, that is the imaginary number because it has the j symbol. The b is also just a number, okay, but the j is an indication that it is an imaginary number. So for example, we have 2 plus 3j, 2 plus 3j, so the 2 is the real, and then this 3j is the imaginary because it is multiplied by the j, or the symbol of an imaginary number. Next, we have the number system. This is the diagram or chart that shows real, imaginary. When I say number system, that's just the diagram, okay? When it's number system, this was already explained earlier, so it is categorized into two: the real and imaginary number, and earlier we have explained the classifications of a real number, right? Okay, and also we have also explained the imaginary numbers, the I. Okay, so that's just the number system. It's just the diagram itself, or the chart. Next, we have the absolute number. These are numerical value of a number, neglecting the sign. This is a number, okay? Number. I just used hashtag for it. When we say absolute number, for example, we have negative 1 with an absolute symbol. This is the absolute number. This is the absolute symbol, okay? So that will be equivalent to just 1. So if we have negative 7 in an absolute symbol, we'll just use 7. we will disregard the sign, whether it's positive or whether it's negative. Okay, just disregard. Now, when you say fractions, it in the form a over b. A is the numerator and b is the denominator. It's defined as the part of a whole. So these are the types of a fraction. When we say simple fraction, the a and b are both integers. Okay, these are also known as the common fraction. Okay, so the simple fraction are anything that's 1/2, 2/1, 3/4, and so on. Now, when I say proper fraction, these are numerator that has a smaller number. So we have here 1/2. 1 is way smaller than 2, right? Therefore, it classifies it as a proper fraction. Remember, numerator is the upper part of a fraction. Next, we have the improper fraction, where the denominator is smaller. As you can see here, 2 is smaller than the numerator 3. Okay. Next, we have the unit fraction, unity for numerator. When I say unity, that is equivalent to just 1. Therefore, the value of the numerator is 1 for a unit fraction, and then a positive integer for denominator. Therefore, a negative 1/4 is not a unit fraction. Okay. Now, when we say simplified fraction, their GCF or greatest common factor is 1. Okay, is 1. So when we say, so for example, we have 1/2. The greatest common factor of these two is just 1, because you can no longer find the lowest term of these two numbers, right? Unlike if we have 2/4. Okay, the greatest common factor of these two is 2. Okay, 2 times 1 over 2 times 2. Therefore, that will just be 1/2 if you're going to find the lowest or the simplified fraction of these 2/4. Okay. Next, an integer is represented as a fraction. The whole thing is just also a type of a fraction. This is an integer represented as a fraction. Obviously, the denominator is 1. Right? Remember that all of the numbers, like for example the counting numbers and integers are commonly have a denominator of 1, but they are just not oftenly written. So for example, if you have -1, commonly that has a denominator of 1. If we have 0, there's a denominator of 1. 1, there's a denominator of 1. Okay. These are integers represented as a fraction. Next, we have the reciprocal result of interchanging numerator and the denominator. Okay. So for example, here we have the 4. From what we've learned, 4 has a denominator of 1 automatically. So if we're going to reciprocate that, interchange this two numbers, we will have 1/4. So if you have 5/3, you will just interchange 3/5. Okay, next. Complex fractions. Numerator and denominator are fractions, just like this one. 1/2 is the numerator, and then the 3/4 is the denominator. Okay, next. Similar fractions have the same denominator. Okay, for example, here they all have 2 as the denominator, so therefore they are similar fractions. Next, zero fraction. The numerator is 0. So you can see here, no matter what denominator you have, as long as your numerator is 0, that is considered as a zero fraction. Okay, next we have undefined fraction. When we say undefined, the denominator is 0. This is an impossibility because nothing can be divided by 0. Okay, therefore it's called undefined. Next, indeterminate. It has no quantitative meaning. This is an example of an indeterminate fraction. Okay, no quantitative meaning. Next, mixed number. This is a combination of an integer in the proper fraction. Okay, when we say integer, for example, we have 2 and then 1/2. Okay, this is an integer multiplied by a fraction. It can also be an improper fraction, but there is a way in order to convert the improper fraction into a proper fraction in order to have a more proper mixed number. We will not dig deeper to that. Next, we have composite number. Positive numbers that have more than 2 positive whole number factors. So these are products of 6 or more integers. So for example, the number 6, its factors are, of course, 6 times 1 is equal to 6. 3 times 2 is also equal to 6. Therefore, these are the factors. Okay, how many factors are there? We have 1, 2, 3, 4. Therefore, the number 6 is a composite number. Now, the number 1 is the only natural number that is neither composite nor prime. Now, what is prime number? It is an integer greater than 1 that is divisible by only 1 and itself. Okay? For example, we have 2, 3, 5, 7, 11. These have only 1 as their factor and themselves. Okay? Every positive integer greater than 1 is a prime or can be expressed as a unique product of primes and power of primes. That is from the fundamental theorem of arithmetic. Okay? So, number 2 is the only even prime number. You should remember that. Only. Okay? Next, types of a prime number. So we have the natural prime numbers. It only has 2 factors, 1 and the number. For example, 3 times 1. That is a natural prime number. Okay. Next, we have twin primes. These are a set of 2 consecutive odd numbers which differ by a factor of 2. So for example, we have 3 and 5. These 2 are prime numbers. And then when we plot it in a number system, 1, 2, 3, 4, 5. So they differ by a factor of 2 in a way that 1, 2, right? Now, if we're going to extend this number system, we add 6 and 7. 5 and 7. 7 are prime numbers and they differ by a factor of 2 as well. And so is 11 and 13, 17 and 19. So these are twin primes. Next, we also have symmetric primes, or what we also call as Euler primes. Okay, pair of prime numbers that are the same distance from a given number in the number line. For example, the 3 and 5. So these are also examples of the twin primes. Okay, these are also symmetric primes. Next, the 3 and 7. How did it become a symmetric prime? Okay, so if we're going to plot that in a number system, 3, 4, 5, 6, 7. So we have a prime in the middle, 1, 2, and then 1, 2. Sorry. So 3, 4, 5, 6, and 7 have the same distance from 5. Okay, 1 and 1, 2. Okay? They have the same distance, therefore they are deemed as symmetric primes. And so is 5 and 7. Okay? They have the same distance. They're just one step away from 6, both of them. Okay? Therefore, they are symmetric primes. Next, we have the emirp. This is just prime spelled backwards. So prime number that remains prime when its digits are reversed. So for example, 11, 31, 13. So if we're going to reverse that, it's just 31. And 31 is also a prime number. So is 17, if we're going to reverse that, 71, and 71 is also a prime number. So these are an example of emirp. Next, relatively prime numbers. GCF, or the greatest common factor, is just 1. So these are integers that share no common factors other than 1. Okay, so for example, we have 9 and 10. Neither are prime numbers, but their factors together are just 9. Their factors, I mean their greatest common factor, both of these are just 9 times 1 and then 10 times 1, because they only shared 1 as their common factor, right? Nothing else. But still, even though they are neither prime numbers, they are still considered as relatively prime numbers, in a way that when they are together, the greatest common factor is 1. Next, we have the unique product of primes. These have a factor that are prime numbers raised to certain power. So for example, we have 360. It is equal to 2 cube times 3 squared times 5 raised to 1. Okay, so 1, 2, and 3. Sorry. So the factors of 360 are 2, 3, 2 cube times 3 squared times 5 raised to 1. And take note that 2, 3, and 5 are just prime numbers. Okay? They are just raised to a certain power. Therefore, this is considered as a unique product of primes. Okay? Next, let's proceed to the perfect number. This is an integer that is equal to the sum of all its possible divisors except the number itself. Okay, so for example, we have 6, 28, and 496. These are an example of a perfect number. Okay, so the factors of 6, we all know that the factors of 6 are just 3 times 2. So it's just 3 times 2 and then 6 times 1. But take note that perfect number is the sum of all its possible divisors except the number itself. If we're going to add 1, 2, and 3, we will get 6. So that is the perfect number. Okay. So there is a formula in order to get whether something is a perfect number. So this is the formula: 2 raised to p minus 1 times 2p minus 1. So p is the prime number. So for example, we're going to find the perfect number using the prime number 2. Okay, so we're just going to substitute number 2 to our formula, and we will get 6. If we're going to use 3, the prime number 3, then we'll get 28. If we're going to use 5, then we will get 496. If it's 7, then we will get 8128. So these are list of perfect numbers. Next, we have abundant number. These have a sum these are sum of the possible divisors. The sum of the possible divisor is greater than the number. Okay, so for example, we have 12. Okay, so for example, we have 12. We all know as 12 has a factors 12. Sorry, 12 times 1. It also has 6 times 2, and then 4 times 3. Okay, we will going to omit itself. So 1 plus 6 plus 2 plus 4 plus 3 is just equal to 7, 10, 16. 16 is the sum of all its possible divisors. Therefore, it's greater than the number 12 itself. Therefore, it is considered as an abundant number. Next, defective number, or we also know as deficient number. The sum of all its possible divisor is less than the number itself. Okay, so an example of defective number is 1 to 5. 1, 2, 3, 4, 5 are defective numbers because 2, for example, 2. So the factors of a 2 is just 2 times 1. We are going to omit itself is just 1, and it's less than 2. Therefore, it's a defective number. Next, we have amicable numbers, also known as the friendly numbers. Okay, these two integers where each is the sum of all the possible divisors of the other. So the smallest amicable number or a friendly number is the 220 and then the 284. So if you're going to find all the factors of or the divisors of 220 and 284, all of this, then you're gonna add it, you will have 284 when they're added. And if you're gonna get 284, the possible divisors of 284, then you will get 220. Therefore, they're both friendly numbers. Next, we have factorial and then the factorial notation. Product of all positive integers from 1 to n inclusive. Okay, so this is the formula or the recursion formula of n factorial. So this is the general formula, n times the quantity n minus 1. So this was derived from this recursion formula. Okay, so if n is 0, then you'll just have to substitute 0 factorial, and then if you're gonna solve this, 0 factorial is just equal to 1. Therefore, they have concluded that n factorial is just a product of all positive integers from 1 to n. So just a trivia, the factorial symbol, which is the exclamation point, was introduced by Christian Krampt in 1808. Okay, for example, if we have 5 factorial, that's just 5 times 4 times 3 times 2. 5 plus rather. Okay. Now the significant figures or digits it defines the numerical value of a number. So the number of significant digit is considered as the place of accuracy of a number. So the rules is that non-significant if used to place a decimal point. Okay, that is non-significant. And then it starts with non-zero digit and ends with 0 or non-zero. Okay, so these are non-significant. Okay, for example, another rule is that if it's a number, then it is significant. Okay, so for example, we have 16.72. 1672 are numbers, right? Numbers. So they are considered as significant figures. But if it is 0.16.72, then you will omit the 0 because it has no value because it's in the start. Okay, but if it's in the middle, for example, we have 106.72, then you're gonna add the 0. So the significant figures of this number is 5 significant figures. Okay, 1, 2, 3, 4, 5. Okay, but if it has a 0, 16.720, then it has also 5 significant numbers. This is a trailing 0, okay? Trailing 0 with a decimal point is considered a significant figure. But if it's a trailing 0 without a decimal point, then we are going to view the 1 as a not significant value. Okay? Just this. Therefore, 16,720 without the decimal number, this will have 4 significant figures only. Okay? Next, 1.672. It also has 4 significant figures. And then the 0.0016, just like what I've said earlier. If the 0 is in the front, okay, leading 0, then it is considered not significant. Therefore, the significant figure of this number is just 2. Okay, only 2 significant figures. Just consider this, the 16 or the 60. Next, we have the forms of approximation. We have rounding, or replacing the number with another number having fewer significant decimal digits, or for integer numbers, fewer value carrying digits. It can be rounded up or rounded down. So for example, if you have 3.1415 and you're going to round it off to only 3 decimal digits, then it will be 3.142. Okay, it's rounded up because this digit became 2, because the number after that digit is greater than 4. Okay, it's 5, therefore it rounded up. But if it's rounded down, so for example, we have the same thing, but it's 0.1414, and we're going to round it off to 3 decimal digits, then it will become 3 decimal numbers rather, 3.141. Okay, so it remained the same. Now, if you will ask, why was it called rounded down if the digit did not remain the same, right? However, this number was omitted. Okay? If you're going to see it like this, it was supposed to have 4 here. But when you rounded it up into 3 decimal numbers, the 4 became 0 only. Right? It was disregarded as if it did not exist. Therefore, the 3.1414 has higher value compared to 3.1410. Therefore, it's considered as rounded down. Okay? But in this case, it's rounded up because instead of having 115 only, 3.1415, it became 3.142. And we all know that this is higher compared to this. Therefore, it's considered as rounded up. Okay, next approximation is truncation. The dropping of the next digits to obtain degree of accuracy beyond the need for practical calculations. Word is a dropping of the next digits. Okay, always has values lower than the exact values, just like rounded down. Okay, so for example, we have 3.1415. If it's 3 decimal, just like what we have discussed earlier, if we're going to have 3 decimal numbers until here, supposedly if you're gonna use rounding, it will gonna round up, right? It will become 3.142. However, in truncation, this no matter how high this number gets, even if you have 1.119999, and if you want to get 3 decimal, it will still be 1.141. It will not gonna round up, and it will not gonna change. Just copy the 3 decimal numbers, disregard everything. Therefore, truncation is just like rounded down. Okay? The difference is, in truncation, no matter how high the next number is, you will disregard it. Okay? Therefore, the values is always lower than the exact values. Next, we have conversion, getting the equivalent value in another unit of measure with a different unit of measure. Okay, so we have Celsius, or the centigrade scale. So it was introduced by Anders Celsius in 1701. He lived from 1701 to 1744. Okay, so the boiling and freezing point of Celsius is 100, and then the freezing is 0 degrees Celsius. This is what we commonly use in the Philippines. And then Fahrenheit, or the Fahrenheit scale, which was introduced by Gabriel Daniel Fahrenheit. The boiling point is 212 degree Fahrenheit, and the freezing point is 32 degree Fahrenheit. This is used commonly in America. Okay, so this is the formula in converting from Fahrenheit to Celsius and vice versa. Okay, now conversion to absolute temperature. Our absolute temperatures are Kelvin and then Rankine. So when we say Kelvin, it was introduced by William Thomson, which is the first Baron Kelvin. And then the Rankine is introduced by William John Macomb Rankine. So the formula is that if we're gonna convert degrees Celsius into an absolute temperature, these two are absolute temperatures, okay? Absolute. So if we're gonna convert degrees Celsius into an absolute temperature, that will be Kelvin. But if we're gonna convert degree Fahrenheit into an absolute temperature, that will be Rankine. Okay, so just add 273 to degrees Celsius and then 492 degree Fahrenheit. Now for unit angle conversion, we have 4 units commonly used. We have degrees. This is what we commonly use in geometry or trigonometry. So degrees most commonly used. Radians, it is subtended by an arc equal to the length of the radius of the circle. Okay, so this is the definition of radians. If we're going to draw a radian, for example, this is your circle, and then you have this. So this radius, then this one is equal to the arc, the length. of the arc as well. And that whole thing, the angle between these things are the radians. And in one complete revolution of a circle, that's equal to 2 pi. So from this until this, one complete revolution, that's just equal to 2 pi in radians. While in degrees, that's equal to 360. Next, we have grads. This is an angular unit equivalent to 1,400 of the circumference of a circle. Next, mils, or also known as milliradians. So this is a thousandth of a radian, or equivalent to 0.001 radian. Okay, so just a simple table. When our unit is degree, our one revolution is 360 degree. When it's radian, it's 2 pi. If it's grad, that's 400. And then if it's mil, then it's 6,400. Okay, so just a simple trivia. The symbol of pi, which is the ratio of the circumference of a circle to its diameter, was introduced by William Jones after the Greek word periphery. Okay, so that's where the word pi came from. That's all. Comment down below what else do you want me to discuss, especially about electrical engineering. Thank you.